Electric vehicle energy sources technology. As there are four viable energy sources technology for electric vehicles: electrochemical batteries, ultracapacitors, ultra high speed flywheels, and fuel cells. In this lecture, we'll discuss the ultra high speed flywheels and fuel cells. The flywheel can be a low speed flywheel or high speed flywheel. In general, a flywheel system stores electricity as a kinetic energy. Its capacity to store the energy depends on its rotating mass, shape, and rotational speed. The rotating mass is connected to a motor generator that causes the flywheel to accelerate during charging, and it deaccelerates when discharging. So kinetic energy is increased or it's stored during charging, and kinetic energy is reduced or deaccelerate during the discharging. And the flywheel is not in use, it is the idle condition, and it has idle speed. Flywheels generally consist of cylindrical rotor or a dish made up of mechanical or magnetic material, bearings to hold the flywheel mass, a motor generator to charge the flywheel and generate the electricity whenever it is required, and power electronics enclosed inside a low pressure vacuum. The whole assembly is placed into the low pressure vacuum. The vacuum reduces the aerodynamic friction between the flywheel and the air. The use of magnetic bearings affects efficiency of the flywheel. So the whole rotating body or flywheel mass is kept in a vacuum to avoid the friction and frictional losses. Flywheel can have a round trip efficiency more than 80% and self-discharge of less than 3% per hour. Superconducting magnetic bearings can reduce self-discharge to less than 0.5% per hour but require higher capital expenditure. So the cost of the capacity flywheel will increase. So these are classified into two categories: low speed flywheel or high speed flywheel, that is it ultra high speed flywheel. Low speed flywheels are usually made up of metals such as steel and have mechanical bearings. So there are contacts with the bearings, and they have an operating angular velocity in the range of 6,000 rpm. High speed or ultra high speed flywheels are made up from composite and have magnetic bearings to avoid the friction losses. They have magnetic bearings. They have an operating angular velocity in the range of about up to 1 lakh rpm. So this is a schematic diagram shown. So it will have a cylindrical rotor, that is the main part of the flywheel. Then it will have motor generator attached to that big mass, flywheel mass. It will have a hub. It will have shaft to hold that big mass. And at the end, there will be magnetic bearings. And this complete assembly is enclosed into a vacuum container. That's a containment to enclose it safely and to reduce the frictional forces and increase the efficiency. Now, as discussed, low speed flywheel system and high speed flywheel systems are there. Here speed range is up to 6,000 rpm. Here the speed range is from 10,000 rpm to up to 1 lakh rpm. Here low speed we have the traditional material used, steel, alloys, etc. For a high speed flywheel system, they are using the composite materials. Low speed, they can be used for power grids, terrestrial applications. High speed, they can use for aerospace and especially the transportation, that is electric vehicle applications. In low speed, they have mechanical magnetic or hybrid bearings. Here for high speed, it should have only magnetic bearings to avoid the frictional losses. The generator motor assembly will have a synchronous, permanent magnet type synchronous and reluctance motor. Here it will have permanent magnet synchronous and reluctance type of motor generator set. The confinement for this will be vacuum, partial vacuum, or light gas. For high speed, there should be absolute vacuum because the speed is tremendously high and the losses will be more if there is vacuum is not absolute vacuum. The integration of flywheel with motor, there cannot, it is not there or maybe partial. Here it will be full or partial for the high speed. The containment weight is rather higher here for the flywheel system. That is the outer covering, that is the containment weight, is 2 times the flywheel weight. In high speed, the containment weight is 50% or half of the flywheel weight, so it is reduced. So as we increase the speed, weight go on reducing. Cost is higher for the high speed flywheel energy storage system. It is almost 5 times the low speed flywheel system. If you see the different layouts, how the flywheel is used, there are various topologies, various layouts or various schemes. Here you can see a simple, the flywheel motor generators system is there, and that will be the connected to the controller. So from control, it can either take the input, electrical input for the motor and rotate the flywheel, or from the rotating flywheel, it can run the generator and electricity can be supplied to this main drive. So flywheel is especially supplying electrical energy. Obviously, battery is there. So this is a battery flywheel system, a hybrid system where flywheel is used. So this dashed line shows the electric link and solid line shows the mechanical link. So mechanical link is from flywheel to this motor generator, flywheel motor generator. And similarly, from the main drive to the wheels. This is a simple layout. Another possible layout may be the flywheel is connected here to the shaft, and also from the battery there will be a motor generator. So here will be the drive and it will be transmitted via the CVT. So this layout to use the possibility that vehicle could be solely controlled by controlling the CVT, continuous variable transmission, when using certain types of electric machines and no separate machine control is needed. So CVT is there. This disadvantage is that power has to pass through the CVT at all the time, which might be desirable at lower efficiency points. Flywheel and motor generator speeds are always coupled together, due to which the flywheel cannot be independently controlled. So here you can see this flywheel and this motor generator. These speeds are coupled and they are transmitted here. The next layout, that is third topologic, may be slight variation in the earlier one. The CVT is only linked to the flywheel. It is linked to the flywheel, and the motor generator is either directly linked on the drive shaft or via some fixed gearing. So you can see this is coupled here to the drive. The advantage of this layout is that the flywheel can be independently controlled and it can be integrated easily on the existing system. However, the machine needs to be controlled separately. So there is a slight modification in the CVT position. The possible next layout, which was a Kogler concept. Here we can see the electric motor and the flywheel. They are in the Same, they are coupled, same line they are coupled, and then hydrothermal transmission is there, and it is connected to the differential. So the flywheel is coupled to a continuous running electric motor. Here we can see it is connected, which was designed for efficient operation in narrow speed range. Once started, the motor can continuously run when the AV has stopped, and during these phases, it charges the flywheel, which act as load leveler. The benefits are the high power output, mechanical regenerative braking is possible here, extended battery life, and avoidance of expensive motor controllers. As there is an electric motor and flywheel is connected to this, there is no need of a separate motor. The flywheel rotated at moderate speeds from 5,000 to 10,000 rpm, and the transmission was hydrothermal, hydromechanical, which was popular due to its commercial availability. The another possible layout is the G concept, General Electric concept, where the flywheel and AC inductor type motor alternator was to be used as a single unit. So here you can see motor, alternator, and flywheel. It is a single unit. It is connected to the inverter rectifier assembly. One battery is connected here as a hybrid combination and then given to the DC motor generator. The steel flywheel and AC inductor type motor alternator is used as a single unit. The flywheel battery was connected electrically to a bidirectional solid state inverter rectifier. Here you can see it. The DC motor is separately excited. So its field is separately excited. Various modes of operation can be considered, and the load leveling mode in which flywheel battery can be charged by the battery during idling periods selected. The performance of the system is highly independent on the drive. So with this possible, there are few videos you can see on the YouTube. Another is the fuel cell technology. Here you can see a general fuel cell technology in a car where there is a battery, there is a hydrogen storage, there is a fuel cell system, and the fuel cell will give supply to the electric motor along with this battery. Here we can see the operating principle of fuel cell. A fuel cell converts chemical energy of a fuel directly into electrical energy by means of electrochemical processes. The fuel and oxidizing agents are continuously and separately supplied to the two electrodes of the cell for the reaction. So here you can see fuel is supplied to this one electrode, that is suppose anode, and another electrode fuel is also supplied. Say here it is a air or oxygen. And also an electrolyte is necessary to conduct the ions from one electrode to another. So electrolyte is also placed. The fuel is supplied to the anode or positive electrode where electrons are released from the fuel under catalyst. The electrodes under the potential difference between these two, the electrons under the potential difference between these two electrodes flow through the external circuit to the cathode electrode or negative electrode. The thermodynamic voltage of fuel cell is closely associated with the energy released and the number of electrons transferred in the reaction. So this shows the schematic diagram of a fuel cell. The major fuel cell technologies, there can be proton exchange fuel cell, alkaline fuel cells, phosphoric acid fuel cells, molten carbonate fuel cells, solid oxide fuel cells, and direct methanol fuel cells. The electrolytes used are solid in proton exchange fuel cell, also solid oxide fuel cell and direct methanol fuel cell use the solid electrolyte, and other they are using liquid electrolyte. You can see the various operating temperatures for these fuel cells ranging from 60 degrees centigrade to 100 degrees centigrade. Also in few it is up to 1000 to 1200 centigrades. Fuel cell mainly works on the hydrogen. So at one electrode, hydrogen is supplied and another electrode, oxygen is supplied. Fuel supply to the onboard fuel cell is the major challenge for fuel cell vehicle applications. As hydrogen is the ideal fuel for fuel cell powered vehicles, hydrogen production and storage on board are the major concern, major challenges. Generally, there are two ways to supply the fuel to fuel cells. One is to produce hydrogen in ground stations and store pure hydrogen on board. The other is to produce hydrogen on board from an easy carrying hydrogen carriers and directly feed the fuel cells. So either it can be stored and carried or it can be produced on board. There are three methods for hydrogen storage on board. Compressed hydrogen in container at ambient temperature, liquid hydrogen at low temperature, and hydrogen in solid form, that is metal hydride method. At present, hydrogen is mostly produced from hydrocarbon fuels through reforming. Reforming is chemical operation that extract hydrogen from hydrocarbons. During this reaction, the energy content of the fuel is transferred from the carbon-hydrogen bonds to the hydrogen gas. Hydrocarbons such as gasoline, methane, or methanol are most likely candidates due to the ease with which they reform. There are three major methods of reforming. We can have steam reforming, autothermal reforming, and partial oxidation. Steam reforming may be used differently with methanol, methane, or gasoline. Autothermal and partial oxidation reforming are most commonly used for processing gasoline. Non-hydrogen fuel cells. Some fuel cells technologies can directly process fuels other than hydrogen. They are direct methanol PM fuel cell, ammonia alkaline fuel cell, and direct hydrocarbon molten carbonate or solid oxide fuel cells. Now, fuel cell electric vehicles. The design and development of fuel cell electric vehicle is a complex due to the variety of available components and combining fuel cell system with a battery. Different concepts for fuel cell electrical vehicles have been developed and tested or are still being used either inside private companies or in public funded research projects. This concept can be classified into four different categories where it can be fully fuel cell electrical vehicle without any battery. Application is limited. Another fuel cell electric vehicle can be hybridized fuel cell electrical vehicle with small battery supporting or working with the fuel cell. Currently, the concept is preferred by most of industries, now called simply FCEV, since pure fuel cell electrical vehicles are no longer being considered. The third one is plug-in fuel cell electrical vehicles, combining a slightly smaller fuel cell system and larger externally rechargeable battery. So in the sense, plug-in is the battery is externally charged. The fourth one is the fuel cell range extender, in which battery electric vehicles with slightly smaller rechargeable battery and a small fuel cell system to recharge the battery is incorporated to extend the range of the battery electric vehicle or pure electric vehicle. So the range is extended by using the fuel cell. So these are the four possible concepts for fuel cell electric vehicles. If you see the full fuel cell electric vehicle topology, it will be like this. So fuel cell system is there. Then the supply from the fuel cell will given the converter, DC to DC converter, and then it will be given to the AC motor, and finally the motor will run the drive. So here DC to AC conversion is done from to give the supply to the AC motor. So fuel cell electric vehicle only use fuel cells to power the transmission system with no auxiliary energy source. This topology is simple, consists only of fuel cell stack, DC to DC converter, DC to AC inverter, and electric motor. Because of its simple structure, it has the characteristics of being easy to control and realize. Commonly used applications are mainly low-speed vehicles such as forklifts, buses, aviation vehicles, trams, and marine vehicles. So this is the full fuel cell electric vehicle topology using only fuel cell and no support of batteries taken. The another type we can see here, the fuel cell working with a battery. So here is a fuel cell system and here is a lithium ion battery, for example. So called as a hybrid power system or hybrid system composed of fuel cell and batteries is the most common topology. Batteries have the advantage of high energy density and low maintenance and low cost. The average life cycle of batteries is 4 to 6 years. Therefore, this type of hybridization is widely used in production and are most common topology along with fuel cell. Batteries connected to the DC bus after the DC to DC converter we can see here. In this system, fuel cells are used as the main power source to provide most of the power to the load. System has advantage of recovering braking energy so that it will have regenerative braking. However, its dynamic response is slower than the fuel cell ultracapacitor hybridization, which is the one more possible combination of hybridization, that is fuel cell, and we can use instead of battery ultracapacitor. That is the next combination, fuel cell plus ultracapacitor hybridization. So fuel cell is there is ultracapacitor, and DC to DC converter is there to connect to this DC bus, and after inversion it will go to the AC motor. So ultracapacitors have low energy density, large power density, and fast charge and discharge, and life cycle is about 12 to 20 years. Because of the voltage fluctuation of the ultracapacitor is large, a fully active topology is adopted. The system has the advantage of more efficient power recovery and better dynamic response to instantaneous high power demand. It also has the disadvantage of high economic cost and low energy density. As we see, the ultracapacitor will show good power density but low energy density. It cannot supply for a longer time. Therefore, it is not as widely used as hybrid power system with fuel cell and batteries. So mostly fuel cell and battery is the best possible combination. The another combination of fuel cell vehicle will be fuel cell, battery, and ultracapacitor hybridization. So fuel cell is combined with battery as well as ultracapacitor or supercapacitor. So here you can see fuel cell, lithium ion battery, and ultracapacitor. They are connected to the DC bus with suitable conversions, DC to DC and DC to AC converter, and given to the further DC to AC converter if it is a AC drive. The characteristics of batteries and ultracapacitors are considered comprehensively so that they can work in different states. Ultracapacitors have the characteristics that can charge and discharge rapidly with high current but have small energy storage. Ultracapacitors can be used to provide instantaneous power or energy recovery when power required by the total load has large sudden changes. However, due to the complex structure of hybrid system, the strong coupling between the power source, the control strategy of the system is complicated because you can see the multiple sources, multiple conversions are there, and the overall system of fuel cell battery and ultracapacitor is a complicated one.